The next topic I want to cover is start moving into the world of C++. So now we've gone from kind of the late 70s and mid to late 70s and early 70s styles of writing code with varying degrees of success to something that relies on a language intentionally designed to support data abstraction and abstract data types. And so we're going to start here, and I think we'll probably do this to round out today. We're going to start by talking about some examples of data abstraction using C++ features circa 1980 or so, the early 80s. So as you'll see, the nice thing about doing this is it's going to allow us to achieve encapsulation. In other words, we're going to hide the implementation details, and we're also going to be able to create more than one stack. So this is a step forward relative to what we were able to do by using C. And we're going to bring up our, and let's go find this guy because I had him from here before. Let's see, where was this? This would be C++ data abstraction A. So that's what we want to look at. Okay, so let's see how we're doing. This might be the last thing that we're going to cover today. The next topic in this part is very cool, but will take a while to set up. So we may or may not go through it today. I don't want to rush through anything today and have people start zoning out. All right, so here is the example. As you can see, this is going to demonstrate C++'s fundamental or core data abstraction capabilities. So again, this is early 80s. This example is also going to demonstrate something widely known as the rule of three. And if you go, I'll show you a link to the rule of three in a second. The rule of three is kind of the way in classic C++, prior to C++ 11, for ensuring that you take control over creation and assignment of your objects in your classes. This, of course, is also an example of an abstract data type. And that's one of the things that C++ was initially designed to solve, was how to write abstract data types more effectively with better built-in support from the compiler. Okay, so let's take a look at an example. This example is going to define three stacks. Stack S1, which we're going to give a default value of, not a default, we're going to give it a value of 10 to. We're going to have stack S2, which we're going to give a size of 100 to. And then we're going to have stack S3, which we're going to give a default value to. And we'll look at that in just a second. I guess I better be keep myself in the early 80s and do this. So actually, I think I want to say T here because this is still going to be a stack of integers. So while the stack isn't full, we're going to push an item onto the stack. Notice now that we say S1, which is our stack, dot full. We don't have to say stack underscore full and pass the address of a struct and so on. Even though that's really what's happening under the hood, this is using C++'s ability to do member function invocation on an object. And as we'll see, these are all non-virtual methods. They're just good old methods, or basically member functions, as C++ likes to call them. So while the stack isn't full, we push items on the stack. And then while the stack isn't empty, we pop items off the stack. If we do an assignment of stack S1 to stack S3, it all works fine because we've taken care of assignment as one of our rule of three pieces of code we're going to look at in a second. And then notice that because we're going to put the fields, the data members, in the private part of the class, we can't try to access them directly. If we try to do this, it yells at us and says, hey, what are you trying to do? This is a private member. It says top is a private member of stack. So we can't do that. And then the other thing here that's really important is the termination is handled automatically. And we'll see how that gets done with something called the destructor. So we no longer have to worry about calling the initialization method because it's done automatically for us by the constructors that are shown here. And we also don't have to worry about destroying our stacks because that's handled automatically. And we don't have to pass the address of the stack anywhere because that's handled magically by the method call syntax of C++. And we can also have C++ take full control over assignment. So how does it do all these wonderful things, you might ask? Now, again, I'm assuming that most of you know this style of C++. So I'm not going to spend a lot of time on all of it, but I do want to mention a few things just because they set the stage for the more interesting examples we'll talk about tomorrow when we talk about modern C++ and modern C++ class design. Or more specifically, we start to talk about modern C++ class design. So up here, we're going to have a type def into a T, because we haven't gotten to the point yet where C++ has parameterized types. We're in early 80s time frame. We define ourselves a class stack, and this implements the rule of 3. And you can go here to this link to learn more about the rule of 3. And I'll show you what the rule of 3 is in a second. Here is the public interface of the class. I'm defining myself a static constant. I guess actually, if I'm really being faithful to the 1980s era stuff, I probably should do it like this, because back in the 1980s era stuff, you couldn't do assignments like that with your with static consts. You had to do them in some other awkward way. So I'm going to do it using an enum, which did work back in that time frame. So it's sometimes in the mists of time, I forget what era of C++ I'm dealing with. So we'll use an enum and we'll get the same result. Also, I should get rid of the word explicit, because that wasn't supported back in those days either. So what I'm going to do here is I have a stack that takes in a size, which will be the size of the stack. And if you don't give anything, like over here, if you look at main, you'll see that we didn't give it any parameter. It's going to default to the default size. So that's called a default parameter. And those get used quite a bit in C++, and they help to clean up the mess you have with languages like C that don't support default values. I should also point out, for fairness, Java does not have default values either, and sometimes things get a little ugly there unless you use patterns like the builder pattern, which we'll talk about in a whole different context if you take some of my other courses. All right, so that's just a constructor that's used to initialize the stack with a size. That's not part of the rule of 3, but it's just a constructor that's useful to have. These methods here are the rule of 3 methods. And you'll see that the first one is what's called the copy constructor, which takes a const ref, so a const stack ref. And that's going to be used for initialization semantics, which get used both when you create a stack from an existing stack, as well as when you pass stacks by value or return stacks by value from functions or methods. This here is the copy assignment operator, which is used when you do things like this, where you say S3 equals S1. This, by the way, I don't really show an example here. I guess probably what I should do, just for kicks, let's do this. Let's say S4 is set equal to S2. So in this particular case, this is where the copy constructor is going to get used. And we could also show some other examples here as well to demonstrate how that gets used. Let's see, what is the compiler complaining about? Oh, so it's saying we don't actually use it, which we don't, but I'm putting it in here just so I can talk about it. So this assignment operator is used when we're assigning an existing stack to a stack that already has its contents, and we want to make sure we do the assignment correctly. And then the final one of the rule of 3 methods is the destructor. And I think you probably know what that does. It's supposed to clean things up that were, especially things that are allocated dynamically, as we're going to do here. The other methods are pretty clear. We've got push, we've got pop, and then we've got a pair of methods called top. One which returns a non-const ref, which can be assigned to, and the other that returns a const ref, which cannot be assigned to. So you can, this is basically, think of this as kind of read-only, and this as being something that could be assigned to if you so chose to do that. And I'm just mimicking the behavior you would find with classes like Vector that have the same kind of an approach, as well as the C++ stack, which I should mention. By the way, I should also point out, of course, that C++ already has a stack, and I'm just using my own stack here just to illustrate some interesting things without getting lost in the mysteries of C++ STL, which we will look at when we get to the C++ STL part of the course. Here's pop. Pop removes the top item without returning it. Top returns the top item without removing it. Sorry. Pop removes the top item without returning it. Top returns the top item without removing it. So they're kind of inverses of each other. And the reason for that is for exception guarantee semantics. In C++, unlike languages like Java, if you pass things around that have value semantics, they can throw exceptions. And so there's no way of being able to have a method like pop in C++ that both removes an item from the stack and returns it by value. It has to do with exception safety. We'll talk more about that when we get into the exception discussions in the class later. Then finally, we have empty and full. Those are marked as const. Top, in this case, is also marked as const. And const simply means it's a guarantee that says this method doesn't change the state of the object, so it can be called on const objects. We don't have any const objects in this example, but if we did, we could call the empty and full method because it doesn't change the state of the object. Down here in the private part, notice everything up here has been public, so it's visible to users. Down here we have the private part, and the private part is not directly accessible to clients that use this code, although its presence will be noted because the compiler will have to make sure it allocates that much memory in order to store an instance of stack. And that discussion about compiler allocating memory if you have private data members is a very interesting topic. We're not going to talk about it now, but when we talk about object-oriented programming later, it figures prominently in that discussion because you oftentimes, when you use object-oriented programming, want to have no dependencies on the size of your implementation. And there are various patterns, such as the bridge pattern or the so-called envelope letter paradigm or idiom in C++ that you can use to help solve that problem. That's a more advanced topic for the object-oriented discussion, however. Okay, so that's the stack definition of the stack class and its interface. Let's now go take a look at its implementation. And this will show off a whole bunch of interesting things. And one of the things I need you to do for me as a favor is I'm going to show you the implementation, but there's a lot of things about this implementation that are not really correct. And it works for this example because we're having a stack of ints. But if we start to generalize this to other stacks of other kinds of things, really subtle bugs creep in. And I'm not going to try to solve those bugs for you in this implementation because quite frankly, in this era of C++, it wasn't a big deal, really. We're going to talk about this when we talk about generic programming and parameterized types, and then I will really solve this for you nicely. So whatever you do, don't take a look at this code and think, now I have a pattern for writing this kind of stuff. I'm getting you there one piece at a time. By the time we get there, you'll see how the later versions of C++ fix all kinds of weird quirks that, quite frankly, most of us didn't understand back in the time frame at which this code would have been relevant, namely the middle to late 80s, particularly because exception handling wasn't really built into the language at this point. All right, so here is the stack's constructor that takes a size, and what it does is it looks very much like the stack create method that we had previously, except now it's got more formalized syntax where we're saying stack : stack. So the stack : thing just says this method here, this constructor called stack belongs to the stack class. And the compiler needs to do that so it knows what it's dealing with. Otherwise, it would have no idea, what is this stack thing doing? Is it associated with a class? I don't know. So in this case, we're using something very important called the base member initialization section. I will show you in much more detail later why the base member initialization section is so important to understand. Whenever you have fields in a class or data members in a class, you're almost always well advised to initialize them in the base member initialization section. And the reason for that has to do with the semantics of what happens in the base member initialization section versus the semantics that happen within the body of the constructor itself. The body would be this part here. There's actually nothing in the body, nothing in the body. And the reason for that is because we've done all the initialization in the base member initialization section. Very, very important to do this. I hope that you learned about this in your previous C++ class, like 2201. But if not, I'll reinforce it here over and over and over again. So here we assign top to 0, size underscore to size, and then we go ahead and we allocate a new array of t, where t is an int, but it could be t whatever t is, and we go ahead and use operator new. And operator new, of course, is this capability built into C++ that improves upon the error-prone semantics of malloc, where you had to remember to multiply size times size of each element. In this case, that's handled automatically for you by operator new. So new T does all the right stuff under the hood. So that's going to assign stack underscore to a newly allocated array of ints in this case, or T's with our type def. All right, so far, sort of so good. That this actually isn't too bad. Let's now go take a look at the copy constructor. So this is one of the first, this is the first of those rule of three methods that we talked about earlier. So in this case, we're passing in a stack by so-called const ref. And that's just the syntax that you have to abide by for the copy constructor. If you take out you take this thing out, you no longer have a copy constructor. You can't define a constructor like that. So that's just, you just have to memorize that as the syntax. I'm not going to yet talk about the cooler, newer features of C++, like move semantics and move constructors and move assignment. We'll talk about that tomorrow. So this is how you're going to make a copy of an existing stack. And you can see what we do is we go ahead and we use the base member initialization section. We say top underscore is assigned s dot top underscore. So we take the right-hand side s and we copy it. And in fact, if I was really being a good citizen of the world, I would refactor this to rename it and call this RHS. So RHS always means right-hand side. So top underscore gets right-hand side, top underscore, size underscore gets right-hand size underscore, and stack underscore gets a newly allocated object of type T, which is an int in this case, of size RHS dot size underscore. All right, that looks reasonable. And then what we're going to do is we're going to write a little loop that's going to go for I equals 0, I less than RHS size underscore, and we're going to copy each element of the stack on the right-hand side into our newly allocated stack on the left-hand side. This works perfectly fine as long as T is a scalar, like an int or a short or a char or a long. And it should also work for things like doubles and floats. If T is not one of those native types, then we've got problems. And I'm not going to tell you a lot about the problems at the moment because I don't want to spoil the surprise when we talk about this when we get to templates. But just be aware that don't use this code the way I've written it for production software. This is just for illustration purposes, kind of the way things were at the time. Here then is the assignment operator. Now the difference between the copy constructor and the assignment operator is for the copy constructor, the left-hand side doesn't exist. So here we say S4 is assigned S2. S2 already exists, S4 does not, so we're bringing S4 into existence by taking a copy of S2. So there's nothing to clean up. With assignment operator, however, in this case we have, say, S3, which is given the default size of 20 elements here. In that case, we already have an object with its values. And so we have to be careful in the assignment operator to make sure we clean things up properly. And that's exactly what we're going to do. Now, again, this code works, but it only works because we've type def key to int. Do not use this code as a template for anything else. I'm just doing it so I can show you later why it's wrong. So the first thing we do is we come in and we do what's called a self-assignment check. So if we're assigning an object to itself, for example, if we say something like S1 set equal to S1, well, nothing to be done, right? We already have S1. We'll just bail out and skip it. So that's what this is doing. It's taking the address of the right-hand side and comparing it against this. This is just a shorthand name for the object for which this method was invoked. So this, if this doesn't equal the address of the right-hand side, we're not doing self-assignment. Okay, so far so good. Let's assume we're not doing self-assignment. So now we've got a right-hand side. So the first thing we're going to do is we're going to allocate a new object from the right-hand side. We're going to make a copy ultimately of the right-hand side into this new left-hand side. But first we have to allocate memory that's big enough. So we say new t RHS.size underscore, and we put that into a temp variable. Suspend your disbelief for the moment. It's full of bugs, but we can make it work for the moment. We then set stack underscore to null pointer. That was probably a bad idea, but for the moment it's going to work. Then we go ahead and have this little loop, just like we did for the copy constructor, and we're going to copy all the contents of the right-hand side's stack into the temp. Because remember, we've already got, whoops, this is actually buggy. That doesn't belong there. That actually is very buggy. We are going to go ahead and do this. So what? Yeah, that was definitely buggy, and that's a good example of buggy code that I wrote. So down here, once we do a copy from the left-hand side, from the right-hand side to the left-hand side, we're then going to delete the existing stack, because we have to free it up because it already has been given values before. So that'll return it to the free store. And you have to make sure that you use the open, close, square bracket notation. Otherwise, it thinks it's a single object, pointer to a single object, not a pointer to an array of objects. And then we go ahead and we take the temp that we just initialized that was allocated up here at this location, and then we assign that to stack underscore. That works. It's still subject to problems if an exception is thrown here, but we'll come back and deal with that later. And then we go ahead and we assign top underscore and size underscore to the corresponding right-hand size, top and size. In either case, whether we did self-assignment or not, or whether we checked for self-assignment and did not have self-assignment, or whether we had self-assignment, we return star this. So that's, of course, the object for which this method was invoked, and we return it as a stack ref. So this actually allows us to chain assignments together. I don't show that code here, but I could do stuff like this. S2 equal S3 equal S1. I personally don't like to write that kind of code. It's perfectly valid code. I don't tend to do it as part of my personal style, but you should write your assignment operators to allow that because it is common convention in C++. All right, so that's the second of the rule of three operators. Now let's go ahead and take a look at the third operator in the rule of three. And this, of course, is the destructor. And you can see what it does is it goes ahead and it deletes the stack, and it deletes it as an array. By the way, at this point, you should have a lot of ammunition necessary to implement assignment number one because it relies on these capabilities. So we delete the stack, and then we just have a bunch of methods, empty and full, and push, top, and pop. And this code is pretty much like the original C-style data abstraction code we looked at, except that we don't have to pass in the address of the stack explicitly. That's done implicitly for us by the C++ compiler. It generates code that will do that automatically without us having to remember to do it ourselves. So this code pretty much does what you'd expect. We assign to the top element in the stack for push. Top will read the top element off the stack and return it as a const ref or just a ref. And that doesn't remove the item. And then pop will just decrement the count by 1. Now you'll notice that when we do a decrement by 1, we're not actually freeing up any memory at this point. The memory frees are done in a batch here in the destructor. Okay, so let's go ahead and just make sure that everything works properly here. So you can see that it does in fact work properly. And in fact, just for kicks, let's try doing something here to demonstrate this. Let's go ahead and assign S1 to S3. And then what we're going to do here, just for kicks, is we're going to go ahead and copy this code. Except now what we're going to do is we're going to say, while S3 not equal to empty, S3 is going to be popped, and S3's value is going to be printed. And let's just see if this works properly. Hopefully it will. And if we look at the results, lo and behold, you can see that it does the right thing. In this case, it goes ahead and makes a copy of it, and then we'll go ahead and pop those things off. So all is well in C++ land. We managed to get all of our rule of three methods implemented correctly. And I kind of showed that here with this code. And let's clean up the syntax. Okay, so now that you've seen the first example of this, let's go ahead and just kind of talk about it briefly. So the nice thing about this approach is that it will hide the information. You can't access the fields directly. And let me see, I've made some changes in my capitalization scheme along the way. So let me make it stack with a lowercase s. I decided I wanted to be a little bit more in keeping with C++'s way of doing things, which may be a little different from your coding guidelines because those were written by Graham, not by me, and I don't want to perturb that too much. So what are the good things? We get information hiding, we get data abstraction, excuse me, and we can create ourselves a stack which will be initialized with 200 elements without having to remember to do it explicitly. We can't access the private fields directly, which is good. We can have multiple stacks. We can do automatic initialization and termination. The stack constructor is automatically called when we go into a scope that defines an object, and the destructor is automatically called to clean it up. So things look pretty good, sort of. The problems here is several problems. First of all, error handling is still not done properly. We don't have exception handling. Second problem is this code is not actually exception safe. If we were to parameterize it with some other data type whose assignment operator could throw an exception, we would leak memory, like a sieve. We're still limited to a single type of stack, although we can change it by changing the type def, but that's not very generalizable. And we'll see how to remove that limitation when we talk about parameterized types tomorrow. And then the other problem we have here is we still have function call overhead. So we had all these function calls everywhere, and we have not properly used yet C++'s wonderful ability to do inline functions. So we'll talk about inline functions later, especially when we talk about parameters, because you usually don't have a choice. They get inline no matter what, oftentimes. So this gives us a good sense of the pros and cons of the early generation of C++ features for